Hello and welcome to part 3 of MaxIm DL training with your host John Blackwell. Today I'll be talking about image signal and image noise. Image signal being the thing that you want to keep and the noise being the stuff that you want to get rid of in each image that you take using a telescope and CCD camera. MaxIm DL has a number of methods of dealing with noise and getting rid of it, and so first I think it's appropriate to give you an idea of all the different types of signals and all the different types of noise that you will encounter when taking astronomical images. At the end of this, we will then break it down into a couple of other videos which talk explicitly about how MaxIm DL gets rid of noise and how you can do that both in complicated ways and in very, very easy ways. After all, that's what software is for, to make your life easy. First, I have MaxIm DL open here. I've got image of an open cluster, NGC6811. I also have the screen stretch window and the information window on, and in the information window I've set it to aperture mode. The first type of signal that everybody should be most interested in is called the image signal. This is what you are trying to get the most of. This is the actual signal coming from the object or objects that you are trying to image. In this case, it's a group of stars in a star cluster that is sending its light, its photons, hundreds of light years away to us, and we are trying to capture that signal, just those photons, and we're trying to ignore every other kind of noise that may be present in this image. The next kind of signal that we deal with is called thermal signal. This is the CCD's dark current, or the slow and steady growth of signal caused by the heat inside the CCD camera itself. This is typically lowered by cooling the chip, and with very typical, readily accessible CCD cameras, that is done with thermoelectric cooling. It is a method of using electricity to remove the heat from the chip and put it onto a different surface in the chip, usually a big block of aluminum, and that is then cooled off with a fan. The fan blows the heat off into the surrounding environment of the observatory. Other observatories will actually cool their chips using liquid nitrogen or liquid helium, gets very cold, or they will use water and pump water next to the chip, not touching it, but touching that aluminum block, and use thermoelectric cooling and whatnot. The reason that thermal energy causes a signal is because every object that has a fairly substantial density, like you, me, a cat, CCD chips, blocks of aluminum, have vibrating atoms. That's because they have a temperature. So things that have a temperature give off light. They give off photons. Now, it's typically not light that you see. It's usually in the infrared and radio. But that infrared light that your CCD chip itself is giving off is actually something the CCD chip is sensitive to and will record as a thermal signal. In other words, the chip is imaging itself. It seems kind of ironic, really, but it's the truth. We have to deal with that. So the two ways we typically deal with that are by cooling the chip down to as low a temperature as possible. Winter is a great time to image. And also we can subtract that thermal signal easily enough, and we'll talk about that later. The next kind of signal that we need to discuss is called the bias signal. This is actually signal information that is already on the CCD chip before an image is even taken. So every single vibrating atom in there not only has a thermal signal caused by the temperature of the chip, but it also has a signal just by random existence that electrons are bouncing around due to quantum mechanics. They bounce around and it creates a very low level signal. It's really easy to get rid of the bias signal though from your image in the end. You basically take an image that's 0 seconds long and you subtract that from the image that contains your image data, and then you're done. Very simple to get rid of bias noise. Now I'd like to discuss some of the actual noise that we get. And it's interesting that I use different terminology here. The word signal means things that are quite consistent, logical, easily to read, and things that we typically desire because they're constant and we can deal with them in an easy way. Noise is a little bit different. It's caused by things that are more problematic, a little bit more tricky to get rid of, and they tend to be a little bit more random than signal. So in this section, let's talk about that. Let's talk about noise. The first type of noise we need to discuss is the most significant. It's called thermal noise, and this is different than thermal signal. Thermal signal is an average overall increase of the signal on your CCD chip caused by the temperature of the chip itself. Thermal noise is the heat noise caused by inconsistencies in the rate at which thermal signals are generated in the chip. This can also come from components within the imager itself. Inside the camera, there are different circuits like the amplifier circuit and the fan circuit, the thermoelectric cooling circuitry, the reading circuitry, etc. Even the power supply has transformers in it that could cause this kind of noise to be received by your imager. I note very carefully that it's about the inconsistencies in the rate at which thermal signals are generated in the chip. So different parts of the chip will record thermal signals differently, and that is the noise that we're trying to get rid of. And I'll show you that using a frame here, which is a picture of absolute darkness. It's called a dark frame, and you can see the noise is generated here in this signal. Another kind of noise that we try to get rid of is called reception variation. This variation in the chip's sensitivity is caused by inconsistent reception of light, or photons, from the source, like your stars. Examples of this would be clouds in your atmosphere, dew on your lenses or mirrors, or, forbid, on your CCD camera itself. Ice. Ice does sometimes form on CCD chips, and it causes variations in reception of photons. Haze, fog, airplanes flying by, lightning bugs, that kind of thing. A sudden deposit of dust on your filter in front of the camera. All of these cause reception variation. Another kind of noise is called read noise. It's actually caused by errors in the amplifier circuit that reads your signal out of your CCD chip. You can think of the CCD chip as containing millions of little buckets. Each one collects both a quantity of photons of signal and a quantity of photons of noise. And what happens at the end of your exposure is that there's a little amplifier circuit that reads out every single pixel one by one, and then makes that signal larger so that it's a voltage between 0 and 5 volts. That voltage comes out and is turned into a digital signal that we read on the other side in your computer. Errors in that amplifier circuit, little hiccups, sometimes some variation in randomness, will cause the read noise that we're discussing here. The next kind of noise we need to discuss is called quantization noise. This is noise created in the analog to digital conversion of your data. After all, photons hitting a chip create an increase in charge in each of the pixels of your CCD imager. That's really an analog value. It's a continuous value. It could be several thousand electrons to hundreds of millions of electrons. The problem is that computers can't read quantities of electrons. So what happens is each little pile of electrons in each pixel is measured and amplified to a voltage, measuring charge, and then voltage to I guess you could call it a pressure of signal. And then that is run into this device called an analog to digital converter, which in the case of most CCD chips converts the value of your charge to 0 volts for black all the way up to 65536 for pure white. It could be any number in between there, but it's going to be an integer number, a whole value. There is no such thing as a pixel value with a decimal point value like, say, 200.221. It's going to be either 200 or it's going to be 201. It's not going to be any number between those. The next and penultimate type of noise that we try to deal with is called sensitivity variation. It turns out that CCD chips do not have the same sensitivity from pixel to pixel, not even across the whole chip. Some parts of the chip will be a little bit thicker than other parts of the chip, and this is because of the manufacturing process of the chip itself. So the thicker parts of the chip actually can hold more electrons, but they're a little less sensitive to light that's coming in to hit the chip. So this change in sensitivity across the surface of the chip results in some stars appearing fainter than they should be, and other stars appearing a little bit brighter than they should be, dependent on their position across the chip. So you may image a star like Vega in Lyra, and if you image it in the upper left part of your chip, it will have a reading of, say, 100 pixel value, but on the bottom right of your chip it might read 120 for a pixel value. That is sensitivity variation, and there are ways of dealing with that as well, which we'll discuss soon. The last type of noise that I would like to discuss today is called light leaks. This is probably the most insidious kind of noise that you'll ever run into. Yeah, sometimes unwanted signals come from light leaking into your optical path from other sources. This is really more common with open-tubed telescopes. Telescopes that don't have an enclosed mirror or enclosed optical system. That is, they look like skeletons holding the primary in the open air and the secondary mirror in the open air as well. So light can sometimes leak in there from other sources within the observatory, or from nearby sources like cars driving by with their headlights on, or even a firefly can go in between your primary and secondary mirror and cause a light leak into your path. But also bright LEDs or PC screens can get light into your CCD chip. It should be noted that LEDs in particular are almost always extremely bright in the infrared. And guess what? CCDs are also very sensitive to infrared light. So you may think a red or blue CCD for the power on some little box inside the observatory is not giving off a whole lot of light. But lo and behold, it's actually illuminating the entire interior of your dome with infrared radiation, and your CCD camera will pick that up. There are some ways of dealing with that, covering LEDs with electrical tape, disconnecting LEDs altogether, and also putting some tape around the CCD camera. There have been instances in my past where I've had a CCD camera that had leaks within itself. It actually had an LED located on its motherboard inside the camera, and every time that the chip started to take a picture, it would blink this red LED on and off until the exposure was complete. Well, there was a light leak between that LED and the chip itself, which was driving us crazy. The solution, a little bit of black electrical tape, blocked the light. So, light leaks, the last type of noise. So you're probably wondering just what the solution is to maximizing your signal, that is the image signal, and reducing all the other kinds of unwanted signal and unwanted noise. The solution in MaxIm DL is called calibration. Calibration is the process of removing all the noises and increasing that signal-to-noise ratio that we see by hovering our mouse over a star here and looking at the SNR value in your information window. So that is the goal, to calibrate your images and to let MaxIm DL do all the work. And trust me, it will. And be glad you're not one of my students in my astronomy classes, because I make them actually calibrate an image mathematically by hand, pixel by pixel. And I think they're fortunate because they've only got a make-believe image of 4 pixels to deal with. Just think about what you're dealing with. You're dealing with images that may be 12 million pixels in size. This is where computers are really fabulous. They do the work for you. So we'll talk about calibration in our next set of videos.